coefficient of expansion for those two materials is the same out to the 5th decimal place. So they're very rugged against temperature cycles. Here is a new instrument called the TSQ Quantiva. We just added 2 new triple quads, LC triple quads, to our product line last week at ASMS. And here is our entry-level triple quad. They're both API, electrospray, and APCI triple quadruple instruments. And the difference is the sensitivity and the resolution. So, as you might imagine, you start with the entry level. You have a certain sensitivity and a low price. You want a little bit more sensitivity, a little bit more selectivity. You pay a little bit more money, you pay a little bit more money. And we have 5 instruments in that stepwise process. When we're doing quadrupoles, we're doing selective stability rather than selective instability. And so now we scan in RF and DC voltage so that we operate at the apex of this stable oscillation diagram. So everything inside of this yellow or green or whatever color it is line, everything here is a stable oscillation. So at these RF voltages and DC voltages, it's a stable oscillation. As we scan the masses, then the closer to the apex that we are, the higher the mass resolution. So here then is an example of several stability diagrams being redrawn as we scan the RF voltage. And what you see is that the data system tries to maintain the RF and DC voltages as we scan across the mass range so that we're scanning through the apexes of the stability diagrams. And if we do that correctly, then a triple quadrupole or a single quadrupole is a constant peak width instrument. So what actually causes the separation in the first place? Here is a diagram of looking at the quadrupole rods from the end. We tried to draw these as hyperbolic surfaces again, because hyperbolic surfaces